Okay, off we go. So last time we were talking about the chain rule. I want to talk about some variations, little tricks, little landmines, things to be worried about, various related ideas. The first one I'm going to point out is be really careful about confusing variables. It's surprisingly easy to do. So for example, let's look at this single variable question. Right? Seems like a nice, easy question. Function given, nothing wrong with this as a function. Fine, perfectly reasonable. G, second function given, perfectly reasonable. There's nothing wrong with this as a function. And to the question of how to compute the derivative of the composition, you might be forgiven for remembering that derivative of a composition is the product of the individual derivatives, right? And you can compute those individual derivatives pretty easy, but it gives you the wrong answer. Now, okay, to be fair, this is a little fast and loose right here, a little careless, right? But it can be fixed. The fix is to realize that G prime is not evaluated at x, it's evaluated at f of x. And I'll point out when I was in school and learning this for the first time, I thought, okay, wait a minute. I'm just supposed to, everywhere I see x, I'm supposed to put f of x instead? That's weird. How am I supposed to keep track of that? That's so confusing. I was never really happy with that. Now, that does give you the right answer. Right? You can see if you plug in f of x, namely x squared, into the g prime function, then everything works out, right? You get the x squared, which gives you, again, what you need. Okay. I guess that's fine. But really, I think this, worrying about this confusing idea of making sure you plug in the right thing, or worse, forgetting to plug in the right thing, you can bypass the entire thing with one easy little step that arguably you should just do for philosophical purposes in the first place. And that is to don't allow yourself a confusion of variables situation, and I claim that's what happened here. So let's look at our diagram. We have this function f, the output of which we plug into the function g, and real quick, I'm just going to point out that if the thing that comes out of f is called y, it certainly can't be called x, right? X is what goes into this function f. You can't have the same thing be what goes in and what comes out. That's no fair. Obvious impropriety, right? So if what comes out is called y, what comes out of f is called y, well, then shouldn't that be the name of what goes in to g? Because that's what we're doing. The thing that comes out of f is supposed to go into g. So said differently, I should rewrite this function g that had previously been written in terms of x. I really should rewrite it in terms of y. Now, some students do get a little weirded out by making this transition. Can I really do that? Can I just rewrite g, which was in terms of x, in terms of y? Of course you can. The variable that you write it in terms of, this is what we call a dummy variable. It's a placeholder, right? If you think about what this function g actually is, g says, whatever you give me, I'm going to cube it. It doesn't matter what you call the thing that you cube. It's just the act of cubing, right? So rewriting g in terms of a different dummy variable is not a problem. It's perfectly legal, perfectly fine. And if you do that, when you do that, rewriting, let me do this. Let me zoom. There we go. Rewriting g in terms of y instead of x. Everything just kind of falls into place. You can be as casual as you want with your notation. You can write down this, for example, the derivative of a composition, the product of the derivatives. Don't worry about what's evaluated where. The notation will keep track of it for you, right? G prime is 3y squared. F prime is 2x. oh, wait, I want my final answer all in terms of x. Don't forget I have to then plug in for what y actually is. Wait a minute, what is y in the first place? Oh, yeah, y is what comes out of f. Y is x squared. And so taking this formula for y and plugging it in there for the y that we have, or if you prefer there for the y that we have, notice that we get then the final correct answer. So I didn't have to worry about, wait a second, do I plug in the x, do I plug in the f of x? I don't have to worry about that at all. Just don't confuse your variables and the problem disappears. So I think that's really good. Now, I suppose you don't have to do this, but again, you're setting yourself up for a risky moment if you don't. And again, I think it's just good practice. I mean, how can you write a diagram in the first place if you have a confusion of variables that remains in your solution? Okay. All right. Now, so there is a multivariable version of this. It's a little bit less obvious in the multivariable case because there's so much else going on. You're not multiplying Calc 1-esque functions. You're multiplying matrices, and you got to worry about which are the columns and which are the rows, etc. When I'm taking partial derivatives, which is a constant, which is a variable. There's just various other things distracting your attention, and it's easy to oops and kind of forget about this. So notice in this example here, where again I have two functions given, and I want to compose and find the derivative matrix. Notice that the first thing I've done, so that I can remove this one item from my things to worry about list, right? Very first thing I do is rewrite G. So recognizing that f takes x and y as its inputs, then the things that come out of f, I can't call x and y. I'm going to call them something else. I'm going to call them u and v. Again, it would be crazy to call those x and y. Right? Okay, well then, if what comes out of f are called u and v, well then likewise, that should be what goes in to g. In other words, I should rewrite my function g. Same exact function, not changing the function, but I should rewrite it in terms of my newly chosen u and v intermediate variables. Everybody good? Okay. And then, just like in the single variable example above, off you go. Right? Here's the derivative matrix for f. Here's the derivative matrix for g. Remember, we are computing the derivative of the composition, for which we have a chain rule. By the way, do be careful of which one is on the left and which one's on the right. Don't forget that's an easy oops situation. And notice that I have, oh gosh, possibly even deliberately written f on the left, even though its derivative matrix belongs on the right here, right? And I wrote g on the right, even though its derivative matrix really ought to be on the left here, right? So heads up, that's part of your responsibility as someone applying the chain rule to think it through for yourself. Don't trust how it's written on the page. That would be completely mathematically irresponsible. Make sure to think it through. Make sure to get things in the right order. Okay. All right. The last little micro detail is, before we celebrate, notice that this expression that we have for this product, which you can multiply out, I guess, notice that it has, for example, a u in it right there. I want to rewrite that in terms of x's and y's. Again, you can see right up here that u and v both are functions of x and y. So let's just plug in. Don't forget, again, the whole point is that u, being the first input for g, is also the first output from f. And so that literally tells me exactly what to plug in where u is in that expression. And then likewise, of course, for the v. Everybody good? Okay. All right, so do be careful. about confusion of variables. Now, this is a special case of a larger problem. The larger problem is a subtle thing. Let me rewind a little bit and remind you how we got to where we are with the chain rule. We started off thinking about compositions of functions. We motivated the chain rule for composition of functions. After that, we kind of came up with dare we call it a rationalization, an alternative point of view on how to think about composition of functions, and with this business about intermediate variables. And then if you take your composition of functions and write it as a diagram, then it's easier to keep track of where the terms come from. And that's nice, and I like it. I'm all for it. Here's where it gets dangerous. A lot of students mistakenly then think that any diagram, any directed graph, anything looking like this, for example, that you can just apply the chain rule to this, and that is not true. We have not addressed questions like this at all, and I don't want to, because there's millions of different kinds of directed graphs, and which variable's a function of what that could be sort of awkward, like this is. I'll elaborate on the awkwardness in a moment. And they're all a little different. So what I want to point out, and that we really should restrict ourselves to in this class, is that the only chain rule we know is for compositions of multivariable functions, not for any graph that you can think of to write down. Right? Compositions of multivariable functions. And when, in fact, you are composing actual multivariable functions, so here's this function called f, and here is this function called g. If you are, in fact, actually composing these functions, then there's several things you got to do for this to even make sense in the first place. And, of course, try not to confuse your variables. That's an easy one, right? But also make sure that your variables that are the inputs for any given one of these functions are actually independent. Now, good news, they are, no problem. The inputs for this f are x1 and x2, right? No problem. The inputs for this g, y1 and y2, neither one of these is a function of the other, no problem. So that's all good. The last thing to be worried about, and this is where the problem comes up over here, I need for the variables that come out of f to be the same as the variables that go into g. Again, that's what composition is. And composition of multivariable functions is the only context for which we know a chain rule. Right? So, in fact, if you look at this situation right here, I don't see any way to view this, in fact, as a composition of multivariable functions satisfying all of these requirements that should follow immediately if you are, in fact, composing functions. Right? So here's the most glaring, for me anyway, problem. This Z1 right here, what is that supposed to be a function of? Well, I mean, I can look at the lines that go into it. It appears to be a function of x1, y1, and y2, but these are not independent. Right? y1 is a function of x1. So, for example, in this context, I cannot make any sense out of, let's see, but just for, let me just circle this real quick. I cannot make any sense out of the partial of z1 with respect to x1, because let's think about what should this mean, partial of z1 with respect to x1. Am I supposed to be holding y1 and y2 constant? That's what you do with a partial derivative, right? But I can't. Because if x1 is changing, well, y1 comes from x1. So if x1's changing, y1's going to be changing too. I can't just hold it constant. So I don't even know what this means. This is a problem. Everybody see what's ugly about this? Okay. Now there's a fix for this. I can't state broadly that the following fix will fix any such problem. Again, there's too many to think about. But it'll certainly fix this problem, and it'll fix anything you're going to need to worry about in this class. And it goes as follows. Let's look at this example here. Various variables given as being functions of various other variables. And if you were to take all these equations and document what's a function of what and make the corresponding diagram, you get exactly this diagram. And here's what I'm going to do. I'm going to insert a new variable into this diagram. I'm going to insert a new variable kind of right there. It's going to be, in fact, just x1. You see the, oh gosh, let's see here. I guess I better do, here we go. So it's x1 star. It's literally just x1. You can see my formula for it right there. x1 star is just x1. Now notice everything just kind of straightened out. Right? Now I have literally a composition of unambiguous, clear, multivariable functions. Right? Having done that one little thing, now these are functions of those, and these are functions of those. No problem. There's the f, there's the g, and now we can totally do the chain rule. Pick your favorite implementation of the chain rule. No problem. Kind of a little fast one to pull, right? Rewriting z1, which had been given as a function of x. I'm writing it now as a function of x1 star. You see right there, right? Wrong color. Sorry, orange. Doesn't change the formula for z1 at all, but it does allow me to view I don't know what that means, to rewrite it as no problem. This means exactly what it says it means. Okay, so be on the lookout for that. Please don't try to, kind of invent your own chain rule as seems reasonable to you might apply to a diagram that you just made up, right? That isn't a composition as written. That's super risky and unsupported by what we're doing in this course. Yeah.
So for the example where you set x1 star to x1,
yeah,
would the output, like with the domain or the codomain chain, would that be a R2 to R3?
Well, it's what I'm doing is what I had originally. There was no domain and target because I don't see any multivariable functions here, right? So this is just a relationship between various variables, and oh my God, right? So by introducing this extra variable, now morally the same diagram, right? Now I can actually say, oh yeah, all of this here, that's my multivariable function called f, and I can ask what's its domain and target. Does that make sense? So it's not like it changed, it's that now I can even talk about it.
Right, okay.
Yeah, yes?
Why don't we have to rewrite the x1s in the y equations?
Because there's no problem, right? In other words, y1 written as a function of x1 and x2, that's fine. This is a function of those, no issue. So there's nothing to be fixed, basically. Is that cool? Yeah, okay. All right. Okay, a little bit of good news follows from this. When you write down your usual chain rule, by the way, notice we're looking here at the partial of z1 with respect to x1. Again, there's three paths. There's that path, gives that term. There's this path, gives this term. There's this path, gives that term. Notice, handy, I find myself looking at partial of x1 star with respect to x1, representing this partial derivative right here. And of course, that's a very easy partial derivative to take. It's just 1. And so that factor kind of disappears. So, and then everything else, you take the appropriate partials. This is all sort of arithmetic beyond that point. Okay. All right, so heads up for that kind of nonsense. Okay. Moving along, let's talk about second derivatives. I have entertained different ways that I might formalize this and write like a theorem or something, and I think it's way more trouble than it's worth. It just doesn't serve any real purpose. Much more useful, much more practical, much more handy for the experiences that you're going to have in your futures is to just kind of get the hang per the following example and then just, kind of follow the pattern that you'll see here. And I think this is just fine for our purposes. I'm going to go through this example, but first I want to point out what the key point is going to be. And here it is. If you have that z is a function of x and y, such as you can see in our example that we're about to do, well, then the partials are also functions of x and y. And we talked about this a while ago when we were talking about higher order partials, right? So this is not a new observation. But this is going to be the thing that makes it all work in the end. Okay. All right, now, there's a lot of details in this. So off we go, bunch of details. Z is a function of x and y, so noted in our diagram. R and theta are our usual polar coordinates. Remember now what that means. That means that x and y are functions of r and theta. Remember, that's our point of view, my favorite point of view anyway, on how to think about polar coordinates, is that x and y are functions of these, what we call polar coordinates. Okay, so again, looking at our diagram, we see we have a clear, no problem composition of multivariable functions, and the question is to compute this second partial. Notice it's a second partial of z with respect to r, right? So second partial through a composition. All right, and the way we're going to do this is one step at a time. If you need to do two partials, the first step is to find the first one. All right, so let's take one partial first. Partial of z with respect to r. Two paths. There's the x path. There's the y path. Yawn. This is exactly like previous examples we've done. A couple of notational observations, I guess, real quick. We're using literally the usual polar coordinates. So I can tell you exactly what the partial of x with respect to r is. I mean, x is just r cosine theta. And the r partial is just cosine theta. Likewise, this becomes sine theta. Yeah?
So for the diagram, x is a function of r, but y isn't it also a function of theta?
It is. It's just not relevant to what we're doing here.
Okay.
Because I'm just looking at the partial with respect to r, which is going to mean theta is going to be a constant.
Okay.
Yeah, that's all. Yep. Yeah, so you can see how the diagrams can get kind of ugly sometimes, and just to kind of, sometimes you have to make tough decisions about what a part of either a diagram or a figure. What do I have to put in there, and what just makes it look more confusing?
Okay.
Yeah, that's all. Yeah. Okay. Notice as well that I am choosing to rewrite the partial of z with respect to x using this subscript notation. I'll say a word about why I'm choosing to do that in just a moment, and likewise there. Okay. All right. So we've taken our first partial with respect to r. Now to get the second partial with respect to r, we're going to take the r partial of the r partial we just computed. Okay. And let's look and see what happens here. A little concerned about what to do with the. Let's see here. Let's look at this term here, for example. What am I supposed to do with this cosine theta here? Okay. Well, make sure to always keep in mind the diagram as we have it so far. And keep in mind what a partial derivative is and what that says about the roles that different variables are playing. And if you are taking a partial with respect to r, that means that theta is a constant, as we just noted. And if theta is a constant, then in fact that means that cosine theta is a constant also. So that's this cosine theta here, it's just a constant because we're taking the partial with respect to r. Everybody happy with that? Lucky break, by the way. Let's take a moment to appreciate our good fortune that this product here didn't have any r's in it. Right? If it had r's in it, then I would have a product rule situation and I'd have to expand using the product rule, and it didn't come up here, but it'll come up in other examples. So anyway, be on the lookout for that. It's just the product rule. But anyway, again, in our current situation, this being a constant, we can factor it right out, and I find myself now just having to think about the r partial of zx. Okay, is everybody with me so far? All right, here comes what I consider to be the key trick. When I entertain this question of the partial of zx with respect to r, and if I'm thinking about it on this diagram, things get really confusing. Partial of zx with respect to r. Am I supposed to view z as being a function of both x and r? Wait a minute. Are you telling me that I'm supposed to view this as being a function of, I guess, all of these? Well, you can't do that. Again, these are not independent. Some of these are functions of the others. What does this even mean? Right? Very confusing, very disturbing. Easy resolution. As we noted up here, if you have a function of x and y, then its partials are also functions of x and y, and that's all I'm going to do down here is just recognize that the partials of z are indeed functions of x and y, and so I add them to my diagram accordingly. And that's all you have to do. Everything else is just a matter of keeping calm and following the rules and moving slowly and carefully. Everything else will fall into place. That's the big trick, though. When you take partials of z with respect to its inputs x and y, those partials themselves are functions and should be added to your diagram. And now everything, like I say, it's all going to fall into place. For example, let's think about partial of zx. There it is. With respect to r, okay. And I have apparently two paths. There's the x path, that gives me my x term. There's the y path, that gives me this y term. And altogether, that's what this mysterious, scary-looking partial thing, how do I even interpret this? No, it's just this per the diagram. Is that cool? Yes?
So that's kind of how you got z of x for the partial of z with respect to x?
The what now?
Like for the above, like the partial of z with respect to x.
Partial of z? You mean like way up here?
Yeah.
Okay.
It's just z of x.
It's z sub x, yeah, that's right. So it is a partial, but it's also a function. And so rather than viewing it as a partial of a function, I'm viewing it as a function itself, and therefore I can treat its values as a variable, and thought of as a variable, I can just play the usual chain rule games. Is that cool? Mm-hmm. Yeah. All right. Notice the cosine theta sticks with it, comes along for the ride. It's a multiplicative constant. It does what multiplicative constants do. Okay. Like I say, that's the big point. Now there's a bunch of stuff to keep track of. You've got to do the same here for the partial of zy with respect to, zy with respect to r. Right? And again, there's two different paths, and each of those two different paths gives you two different terms. Intermediate variables are, again, x and y. Two paths, two terms. Right? Again, the constant sticks around, as multiplicative constants do. And it's all over but the shouting. So at this point, again, easy notational choices here. That's just notation. Z, in fact, is directly, no composition required. Z is directly a function of x and y. So, for example, the y partial of the x partial. Yeah, cool, zxy. No chain rule required. There's no composition between those variables. Again, easy polar coordinate partial derivatives. Nothing to worry about there. And you multiply them out, collect terms, et cetera, and it simplifies very nicely to this. Everybody all right? So we have successfully, let me summarize what we've accomplished with all of this. We have turned, there was a question about a second partial through a composition, and we have written down now how to compute a second partial through a composition in terms of stuff that doesn't have any composition at all in it. Zxx, yeah, z is immediately a function of, among other things, x. There's no chain rule to be done in here. And likewise, every other factor in every other term. We've gotten rid of all the compositions. So everything down here is immediately computable. Is that all right? Everybody happy? Now, there are some big questions that follow this. Namely, when am I going to need this? What is this good for? Are we just playing fancy games? Right? Well, there are some pretty great uses of this. I'm going to show you my favorite one. This is from my physics days long ago. A little bit of background. There's this thing called the Laplacian operator. You may or may not have seen this in a physics class. If you haven't yet and you're an engineer, then you definitely will eventually. It's really, really important. It's the primary mathematical object that explains that is used in models that explain how waves propagate, how heat moves through space, how electrons move and behave in a different electric potentials kind of environment. So there's a tremendous amount of applications. It can't be overstated how important this is. And I claim that even though it is very compactly and nicely written, as I've got it written here in rectangular coordinates, I claim it's really useful to rewrite it in spherical coordinates, which I claim ends up looking like this. And that is not obvious how this, talking about the partials with respect to x, y, and z, is equal to all of this, where the partials are with respect to these spherical variables. Now, notice what I've got here, right? I started off with f being a function of x, y, and z, and I then remind myself that spherical coordinates says x, y, and z are functions of rho, phi, and theta, and you'll notice that we again have a composition, and all these derivatives inside of this monstrous rewrite, they're all composition derivatives, including, well, depending on how you look at it, several second partials through the composition. Now, how do you actually show that this works? There is a lot of work that goes into this, and I'm not encouraging you to do this. Very often I'll say, yeah, this is a healthy exercise. This will, build character. You should totally do this calculation. Not this one. This is too much. It is hard. It's a lot of details. I would definitely forgive you for not doing it. And I'm glad that I got mine done and I don't ever have to do it again. But the big idea, second partial with respect to with respect to a spherical variable, it's just a rip-off of what we did over here, where we computed a second partial with respect to, well, here it was a polar variable, but again, morally the same. It's just polar coordinates instead of spherical coordinates. Same big ideas. Right? And if you go through and rewrite this, and then likewise for all of the other various spherical partials there, and you put it all together as written, and you do a tremendous amount of algebra and stuff, what you'll find is you get exactly this Laplacian right here. Okay, you may be unpersuaded by this. Great. We have successfully now turned a hard expression into what appears to be a much harder expression. And making lives more difficult is not what we're here for, right? So let me try to persuade you that this is a win. And it's a massive win. Here we go. Reminder, why are we interested in the Laplacian? Well, for many, many reasons. The Laplacian, among other things, it helps us understand gravitational potentials and electric potentials, voltage, as you may understand it in a physics context. So, okay. Apparently, I'm going to need to understand this equation. I'm going to need to be able to plug in a function into this equation and see what I get, and I hope I get 0. 0 is what makes it work, right? So I don't know that I have the right solution, f, until I know that equation works. And I would like to try this function right here as my f. And why would I want to try that f? Well, because it turns out that that's the right answer, right? And so let's start one of many right answers. So let's think about how to actually do that, right? How would I plug in that function to the Laplacian operator? What do I get? Okay, well, the Laplacian we have in rectangular coordinates and spherical coordinates. This function here, f, you'll notice I can write it in rectangular coordinates or spherical coordinates. And so if I need to compute all of this business here in purple, I can either do this or I can do this. Now again, I'm pretty sure I haven't made a sale yet. Right? You look at these two options. Which one of these two things would you rather compute? Would you rather deal with, some rectangular? Okay, there's a square root. Okay, fine. Okay, there's a fraction. Okay, fine. But it doesn't look all that bad. And I think that would be a generous statement. I think it's actually pretty annoying. Y'all are going to do this calculation, by the way, at some point. I forget exactly when in this course, but it's going to come up, and it'll take you a page of algebra, and it's got some tedium to it. And everybody has to do it once in their lives, right? So here comes yours. I did mine, right? So annoying, doable, but not pleasant. And then you think to yourself, well, then this one down here must be a nightmare. But it's not. This one down here is easy. This one down, we're going to do this one on our head. It's that easy. It's super easy. Look how easy this is. Let's take this one term at a time. We'll start with this third term over here. Notice the very first thing that I need to do, apparently, is take a theta partial of that function that doesn't have any thetas in it. That's an immediate 0. And this whole term disappears. I mean, it's very straightforward, right? You're taking a theta partial of something that doesn't have any thetas in it. 0. All right, let's look at the next term. Let's look at all of this, yikes, as applies to that. Again, the very first thing I need to do is to take a phi partial of an expression that has no fees in it. Again, zero, poof, gone, right? Now, I want to emphasize, we've barely lifted a finger, and we've computed already, I think I would call it the two scariest looking terms in this expression. That cool? Everybody on board? All right. So last term, let's look at this applied to that. And okay, here, all right, it's not going to be immediate here. I have to start off with the row partial of a constant over row. All right, it's not zero. It's like, what is it, minus k over rho squared. So there's a factor of 1 over rho squared. Then apparently I'm going to be multiplying that by rho squared. I am then, it would seem, going to be taking a row partial of, well, wait a second, there was a rho squared that got multiplied by a 1 over rho squared. The rows cancel. Row partial of something that has no rows in it, 0. We're done, we win. Very easy calculation when you put it all together, right? So that disappears too. Casual glance, as opposed to, I'm going to say, a pretty significantly inconvenient bit of algebra up here. So I think this is a big win. Who do we credit for this big win? This is a result of knowing this formula, which comes only from understanding how to apply the chain rule to a composition with higher order partials, as we did on the previous page. So all of this is thanks to calculations like this. Everybody happy? All right. Okay, on to 2.6. So I want to remind you of some stuff that we've done with partial derivatives to start off here. So we have understood partial derivatives as follows. Partial derivatives are slope of the graph. It's a multiplicative factor. It's what you multiply by input change to get output change on the assumption, blah, 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 right? And so those are, I guess, maybe our two primary sort of geometric interpretations. But here's some other facts, true facts about partial derivatives. I can compute a partial derivative with this formula, which doesn't look very appealing, I grant you. But just as a truth, independent of how useful it is, the gradient is made up of all the partials, and dotting with a vector that's mostly zeros and a single 1 would then give you one of those partials. So true, but not clear how useful that is. So we'll come back to that in a minute, but there's a true fact about partials. And then here's another interpretation you could make of partials. This one, let's just kind of talk through what this is saying. Actually, let me zoom in so we can see this better. If I can get this to, oh gosh. Okay, there it started to go. Okay, let's talk through this formula right here. What does a partial derivative say? A partial derivative says, all right, I'm going to presume that I'm at the point A, and this says I'm only allowed to move in the xi direction, and as I move in the xi direction, I want to know how f is changing. That's what a partial derivative is. I need to move exactly in the xi direction, and then keep track of how f changes. Okay, now let's think about this expression over here, and notice this little parametric line on the inside. Notice the direction vector has us moving exactly in the xi direction, and taking a derivative with respect to t says, okay, as t changes, as I move in that ei direction, then how fast is f changing? So we don't need to worry about the algebra that relates the partial derivative to this expression, but just, back of the envelope, I mean, they both say morally the same thing. I'm at a point A, I'm moving in the xi direction, and I want to know how fast f is changing. And I claim that these are actually equal, and I hope that's pretty believable. Okay, now, very importantly, so far, all we know is that these are statements about partial derivatives. Partial derivatives are a very restricted category. This allows only for moving in the direction of one of our axes only. Right? What if I wanted to go in a different direction? What if I wanted to, I don't necessarily want to go exactly that way or exactly this way, parallel to the axes that I've got set up. And I'd probably want to set up my x-axis in that direction, y-axis like so, and z-axis up. What if I want to go that way? Right? Partial derivative doesn't help me. Okay. So here's the rewind I want to do. Coordinates are overappreciated. They're kind of unnatural if you really think about it. Right? Coordinates are something you make up. If I want to talk about a multivariable function in this room, for example, and my favorite example is temperature because it's something that we can kind of relate to, and we're comfortable physically with the idea that temperature depends on where you are. It's an easy to sort of get multivariable function. If I want to talk about the temperature at this location right here, that's a meaningful concept without setting up any coordinates at all. Right? Temperature depends on location. And I guess you could say it depends on the coordinates if you have coordinates set up, but that's a highly optional. Right? You don't need coordinates at all. Okay, and then furthermore, not only do you not need coordinates at all, you could set up any of a number of different coordinate systems. So, for example, now again, this being a basically rectangular room, right? I think life is good in certain ways if I choose, axes kind of with the walls and ceiling in mind, right? And that, suggests, but I don't have to do that, right? If I wanted to, instead of using these as my axes, I am perfectly allowed, if I should so choose, to use these as my axes. No problem. Nothing wrong with that at all. There's my x-axis, there's my y-axis, and my thumb here is my z-axis. Now, it's not clear why I'd want to do that, right? But here's the thing. If I set this up as my axis system, notice my index finger. This is now a standard basis vector. This is now the direction of an axis, right? It hadn't been. The axes had been like this, right? But now this is in the direction of a coordinate axis. That means that as I move in that direction, I am literally talking about a partial derivative with respect to my new coordinate system. And any unit vector will play the same, right? If maybe I want to go that way. Okay, well, instead of that or this, okay, I'll choose this as my axis coordinate system. And now, again, the direction I want to go is my standard basis vector. So the big thing to realize, and again, it seems restrictive, when you say, oh, these interpretations, they only apply to specifically if you're going in the direction of one of your coordinate axes. Just keep in mind, you don't have to stick with the same coordinate axes you may have arbitrarily chosen in the first place. Any direction can be one of the directions in a perfectly acceptable coordinate system, right? So the big takeaway then is that these four features make sense and are equal to each other no matter which direction you're talking about, as long as you're talking about a unit vector. Because no matter what direction you're talking about, that direction could be a direction of a coordinate axis. Okay, all right, so that's the pitch. So now with that in mind, again, any other unit vector. Take your pick. This formula, that formula, slope of the graph, multiplicative factor, these are, again, all the same thing. And now, annoyingly, okay, I can't call them partial derivatives because I did, in fact, pick some actual coordinates. I do really want to stick with the convenient coordinate system, right? The fact that I could change to a different coordinate system doesn't mean I actually want to. So I want to keep my coordinate system, so I can't call this a partial derivative. But this is just semantics at this point. I can call it something else, and the term we have for this is directional derivative. So the big idea here is that when you hear the term directional derivative, represented by this notation right there, when you hear the term directional derivative, in your mind, you should be thinking, okay, so partial derivative. I mean, morally, it's just like a partial derivative. It's just that it's a partial derivative with respect to a different coordinate system that I don't want to have to actually deal with directly. But in terms of interpretation, directional derivative, think of it just like partial derivative. And the beautiful thing about it is, with all this set up, directional derivative, we have a notation now, we have a definition, we have a formula that's awful handy for computing it, right? How else would I certainly don't want to have to actually write down a parameterization and plug in the parameterization, and oh gosh, the algebra on this could get a little unwieldy. But easy peasy formula, just dot product with the gradient, nothing to it, right? And I have some free interpretations. This thing, directional derivative, again, morally, it's a partial derivative, effectively. Of course, it gives you slope of the graph. Of course, is a multiplicative factor. That's what partial derivatives do. Okay, let's see here. How are we doing on time? Oh, I'm sorry. So that clock is just wildly slow, fast. Apparently, I've gone over time. We'll pick up here on Wednesday. See y'all later. Have a good one.